So 72 you can look at that as having factors of, just think of two numbers that multiply to 72. 2 and 36. All right. And then you look at the 36 and it's like, all right, what are two numbers that multiply to 36? You say, all right, 6 and 6. Two numbers that multiply to 6. 2 and 3. What you end up with is known as the prime factorization, right? Because 72 is equal to 2 times 2 times 2, so 2 to the third power times 3 to the second power. That's information. With the 96, same idea. Look for two numbers that multiply to 96. All right, 16 and 6 if I'm not mistaken. Four and 4 gives you the 16. 2 and 2 gives you a 4. 2 and 3 gives you the 6. We have a couple of 4s, so I need to duplicate this real quick. So we're looking at 96 being equal to, kind of got a little messy here, but we're looking at 5 of those 2s and a 3. All right, so 2 to the 5th power times 3 to the 1st power, or just 3. And you look at this and say, all right, well, how's that helpful? Well, if you don't write it in power form, it's actually kind of easier to see. But what we're doing is we're doing a little quick comparison between those two sets of factors. The two numbers and their corresponding sets of factors. All right, so that 2 to the third power is really 2 times 2 times 2. Then we have 3 times 3 for the 3 to the second power, as opposed to 2, 2, 2, 5 of them. So what we would do is we'd look at this and say, all right, well, I have 3 2s here. I have 3 2s here. The most number of 2s I have are 3. All right? So for the greatest common factor, I would need to incorporate, that's not a marker. GGF? No, GCF. I'd need to have 2 to the third power, and then I would need to incorporate the most 3s that are in common between the 72 and the 96. All right. So in common between the two, there's only the 1 3. So 2 to the third is 8 times 3 is 24. So the GCF would be 24. All right, that's if you want a procedural approach. I mean, it's not fun, but that's how it all works. As opposed to that, you'd probably prefer a little bit of number sense to say, all right, what is, like in your mind, what is the largest number that I can divide evenly into 72 and 96? Now, you may not come up with 24 immediately, but you should come up with it after, a couple of attempts, assuming you don't come up with it immediately. Now, assuming that you're incapable of coming up with it in your head or on paper, and you don't want to do this, there is a calculator technique. Assuming my calculator wants to open. Doesn't want to open. It's opening. It's just taking its sweet time. Come on. It also works on Desmos. If you go into functions, it's in there somewhere, but you just type in GCF and it shows up. It might be GCD actually. I'll check that out in a second. But in a TI calculator, it's in the math menu under NUM. Scroll down until you find the one that says GCD. And then you type in the two numbers, 72 and 96, with a comma separating them. Comma's right here next to the parentheses. So far, it's been infrequently used to the point where you probably didn't even know it existed. But we'll use it more and more as we go forward. And it'll spit out the GCD, all right? Why it's a D, I have no idea. I used to know, greatest common divisor. It just came to me. Why do they got to be difficult? I have no idea. All right, they could have easily put GCF, but they didn't.
So GCD and GCF are the same thing.
Correct. All right, so it'll give you the value. The calculator will do that for you. All right, the TI calculator. Now, as far as the Desmos calculator is concerned, let's see. Yeah, it's in there. It's under miscellaneous. Function, miscellaneous, GCD, same deal. You type in, and you actually type it in exactly the same way, 72, comma, 96, and it'll spit out the GCD, as they say. All right. So it saves you the time of having to do this this tree diagram. However, I like to do it at least one time, the tree diagram, or tree diagrams, just to show you the rationale behind where greatest common factors come from. All right. So for the second one, we're talking 17 and 59. Says the greatest common divisor is 1, which means that there is no number larger than 1 whole number that divides evenly into 17 and 59. All right. So the GCF would just be 1, which would be not helpful. But then we get to the variable cases, and that's where the connection with the tree diagrams come into play. Because you look at it and say, if I were a student in this class, I'd be looking at this and be like, well, if we could do it on a calculator, why would we do this? This is kind of a waste of time. And you just burned like 10 minutes of class doing this. What was the benefit? It's for number 3. Because looking at it with the powers in mind, and that connection between the powers and the expansion of those powers allows you to determine what the GCF would be in a relatively easy way. So let's actually go back to number 1, and instead of saying, all right, 2 to the 3rd power is writing the 2 out 3 times, 2 to the 5th power is writing the 2 out 5 times, and so on, is there a way that we can do this without writing these expansions out? You know, that's the point, because, it's possible. I don't know. I don't think I would be thinking this, but it's possible that you were thinking this at the time. If I had a number where the expansion was 2 to the 70th power, do I want to write the number 2 out 70 times just to highlight the number of 2's that are in common between that number and another number? I probably not. All right. So what we do is we look at the 2 values that we see in exponential form. We have these 2 to the 3rd, 3 to the 2nd, 2 to the 5th, 3 to the 1st. Between the 2, we have a 2 and a 3. The 2's raised to a power, the 3's raised to a power. we take the 2 that's raised to the smaller power, we take the 3 that's raised to the smaller power from the set of possibilities. So I have a choice here between 2 to the 3rd and 2 to the 5th. I'm going to take the 2 to the 3rd. I have a choice between a 3 to the 2nd and 3 to the 1st. I'm going to take the 3 to the 1st. And if you look at what we did up here, that's exactly how it played out, giving us that 24. All right. So take what we learned there and apply it to the variables. And you see here, now just running through and saying, all right, any variable that's without a power is really raised to a power of 1. I would look at this and say, all right, I got 2 possibilities. From the x's, I'm going to take the one that's raised to the smaller power, x to the 2nd. From the y's, I'm going to take the one that's raised to the smaller power, y to the 1st. And that would be my GCF. Because they're non-numerical, I mean, they're variable, so they are numerical inherently, but we don't know what the numbers are, so we can't do anything with it. All right, so this is as far as we can go. All right, so x to the 2nd, y to the 1st, or just x squared y. All right, so that would be our GCF. So even in the case of variables, it's actually not that bad because, you know, we took the time with number 1 to investigate what's really happening behind the scenes. And instead of saying, I mean, I could do it this one time just to kind of drive the point home. That x to the 3rd, y to the 4th is really the same as saying x times x times x, y to the 4th, y, like why am I doing this? X to the 2nd, y, x, y. So I'm looking for every element that's in common between the 2 sets. This is in common, this is in common, this is in common. We're all out of material in the 2nd set, so nothing else could be in common. So what I have in common between the two sets would be 2 of those x's multiplied, so x squared, and a y, x squared y. All right. Now what we just have to figure out is, all right, well, if we have a binomial or trinomial, quadrinomial, 4-termed expression. I don't know. I never looked up what those are called. Multi-termed expression, how does that come into play? Well, if you're looking at, I mean, there's a lot of examples here. Some of them are pretty funky looking. But it really boils down to the same concept. You're taking the 2 values that make up the expression. I have a 20x to the 2nd and a 15x to the 1st. I'm just looking for the greatest common factor, as in the title of the lesson. But I'm looking for what's in common between the 2 sets. Without getting into the prime factorization, you know, making a whole tree diagram, which would take a little while. I mean, these numbers aren't that bad, but, you know, you can imagine, I mean, if you had like 2 numbers like, let's say 162 and 16,484, I mean, you could be at it for a while. You don't want to get into that. So for the numbers, the numerical parts themselves, you handle that. If you recognize the GCF, like I look at these 2 numbers and I think 5. All right, because I think to myself, what is a GCF? It's the largest number, that's the greatest part of greatest common factor, largest number that divides evenly into the 2 numbers that are given. I'm thinking 5. All right, but if I'm not thinking anything, I go to the calculator. And it'll tell me 5 anyway. All right, so for the GCF, I know there's going to be a 5. All right. Now for the variables, just like we did in the do now problem number 3, I'm just looking for the variable across the board that has the lowest power. All right? Because again, that x squared is the same as saying x times x. X to the first is just x. I'm looking for what's in common between these two sets. All right? I have an x in common, but now I'm out of material over here. I have nothing left. All right? So the only thing that's in common between the two sets is an x, variable-wise. We already accounted for the 5. So 5x would be the GCF. But it says factor each polynomial. Now, there are rules that are indicated on this page, but when we factor, what we're looking to do is undistribute. We spent the whole last unit working on the distributive property. We're going the other way now. It's already distributed. Let's figure out what the expression was before it was distributed. So all I'm going to do here is take each term of my expression and divide it by my GCF. So my GCF is 5x. I'm going to divide it by 5x. But then that 5x becomes a multiplier. You know, just think of it this way. If I said, give me two numbers that multiply to 72, you might not be 100% sure off the bat that it's 2 and 36. So you might think to yourself, all right, I know 2 goes into 72. All right, well, what would be 72 divided by 2? Carry the 1. 36. Oh, so it's 2 times 36. So you carry out the division and then take that number that you had in your mind and multiply it by the result of the division. That's what's happening here, all right? Except we're using variables. So you're saying, all right, what's a number that goes into, well, 20x squared minus 15x? 5x. All right, so divide, carry the 1. 4x minus 3. So you write it as a multiplier and say, okay, well, that means that 5x times 4x minus 3 would give me the 20x squared minus 15x. It's the same idea as, or what are two numbers that multiply to 72? Right? Same idea, more complicated, obviously. Now, the big question would be, how on earth did I just come up with this 4x minus 3? Well, we look at our variables, because the numbers, I don't think anybody's questioning the numbers part of it. 20 divided by 5 is 4. That's easy, right? But when you look at the variables, it's the opposite of the concept that we used when we multiplied variable expressions, monomials. When we multiplied, we kept the base and add the exponents. Now we're going to keep the base and subtract the exponents because we're dividing. All right, 2 minus 1 is 1, 4x to the first power. These are both to the first power. I mean, you could look at it conceptually and say, well, x divided by x is going to cancel out. X divided by x is equal to 1, so it's irrelevant. But you could also look at it and say, keep the base, subtract the exponents. 1 minus 1 is 0. X to the 0th is 1, which makes it irrelevant in that regard also. All right. Bottom line is, we get our answer here of 5x parentheses 4x minus 3. All right. But the process doesn't change no matter how many terms there are. All right. So we can go to a nasty one, like number 8, and look at it and say, all right, well, I need the largest number that divides evenly into 6, 9, and 18. Number-wise, that's not bad. I mean, because you could play that out in your mind. Maybe you think it's 6, but because 6 goes into 6 and 18, but it doesn't go evenly into 9. All right, so you dial it down a little bit. So maybe you say 2. 2 goes into 6 and 18, but it doesn't go evenly into 9. So you say 3, oh, there it is. You know? However, they won't all be this nice. So what do? You could use the calculator, either version of it. But the calculator only works 2 terms at a time. So what we do is we take the 6 and the 9 and compare those. So now we know there's a GCF of 3. So hang on to that. Use that 3 and compare it to the 18. And so that confirms that the GCF is 3. All right? So you work the first 2 against each other, take that answer and work it against the third. All right? Same idea with the TI. Okay, that's weird. Come on. So again, math, NUM, go down to GCD, take the first 2 coefficients, 6 and 9, and you could actually take any 2 coefficients. Doesn't matter. All right, you can do the 9 and 18 if you want. All right, get that answer, and then compare that against the third one.
It's kind of like what we were just doing when there's 3 pairs. Is, multiply the first 2 pairs, and then the product of that multiply the third.
Exactamundo. Very good. So we're good on the numbers. Now we got to take care of the letters. All right. So you just have to keep track of what's going on variable-wise. So I have an x to the first here. Now, hidden behind the scenes here, I got a y to the 5th, but behind the scenes, there's an x to the 0th power. All right, because anything to the 0th power is equal to 1, so it would cancel out. All right, so it's mysterious. It's hidden. All right. So what I'm going to do is I'm going to look at, I have 2 variables. I have x and I have y. I'm going to go across the board and look for the x with the lowest power. I'm going to go across the board and look for the y with the lowest power. So that's going to be 3y to the third. I'm then going to divide each term by 3y to the third, and then just throw that 3y to the third out in front of the whole expression. All right, so I have my 6x squared y to the third, 9xy to the fourth, 18y to the fifth. Each term gets divided by the 3y to the third, with the 3y to the third going out in front of the entire expression. All right. So I'd look at this and say, all right, what do I get if I take the 6 divided by 3? I get a 2. There's nothing to divide into the x squared, so x squared comes along for the ride. What happens if I divide y to the third by y to the third? Cancels out. 2 like quantities being divided. All right, or keep the base, subtract the exponents. Either way, it's going away. It's clever. Nine divided by 3, 3. X isn't getting divided by anything. There's no x in the bottom of the fraction, so x comes along for the ride. Y to the fourth divided by y to the third. Keep the base, subtract the exponents. Y to the first. And just a quick aside on that, when we talk about y to the fourth divided by y to the third, that's saying we have 4 y's up top, 3 y's on the bottom, all multiplied. y divided by y is 1. Y divided by y is 1. Y divided by y is 1. We're left with just a single solitary y. That's the justification. You don't have to do that. It's just worth it to talk about it the one time. All right. 18 divided by 3 is 6. Keep the base, subtract the exponents, y to the second. And so this would be our final answer. All right, but it's the same skill. Same skill as the first example. I mean, it looks more mathy, obviously. But there's nothing more complicated about this problem than number 1. And looking at number 9, there's nothing more complicated about 9 than 8, except we switch the variables, but that doesn't make it more challenging. You look at the numbers. 10, 2 and 14. We have our GCF. The biggest number that goes into 10, 2, and 14. Well, it really can't be bigger than the smallest number in the set. So it's got to be 2. Going across the line, I'm looking for the h variable that's raised to the lowest power, so h to the first. The n variable that's raised to the lowest power, n to the first. That's what I'm dividing each term by. So 10 h to the third, n to the third, minus 2 h to the first, n to the second, 14 h to the first, n to the second. N to the first. Dividing that by 2 h to the first, n to the first across the board. Carrying out that division is really what gets you the rest of the way. As long as you don't forget to throw that 2h to the first, n to the first in front of the whole expression, you'll be fine. Right? So I'd say, all right, what's 10 divided by 2? 5. Then I carry it out with the exponents. Keep the base, subtract the exponents. 3 minus 1, 2 minus 1. All right, so h to the second, n to the second. 2 divided by 2 is 1. Irrelevant, cancels out. Keep the base, subtract the exponents. 1 minus 1 is 0. H to the 0th is the same as 1 because anything to the 0th is 1. Irrelevant. Keep the base, subtract the exponents. N to the first. That's all that remains. Everything else is a 1. 1 times n to the first is just n to the first, or n. It's very systematic. If you follow the I mean, it's very rare in math that a complicated a complicated concept actually has a defined process that works every time. Most of the time it's like, well, in this circumstance it works this way, in that circumstance it works that way. You follow the steps, you get the answer. It's very nice. Sometimes the steps require more work, but it's a good thing. 14 divided by 2 is 7. Keep the base, subtract the exponents. Keep the base, subtract the exponents. So h to the 0th, n to the 0th, 1, 1. 7 times 1 times 1 is just 7. All right. So Yeah, even the nasty ones, they still follow the same process. All right. So as long as you go through the correct approach, you're going to be good. All right. So your homework is to just tackle the problems on page 2 and 3. All right. So I'll put that up on Schoology in a minute, but yeah, pages 2 and 3, and then just remember tomorrow I'm going to be collecting the Unit 5 packet. All right. I'll put all that on Schoology also, but just so you have it on your radar.